friends, my name is Sandeep Mandal from Des Engineering, and today in this topic, the topic is of previous one only, that is steady one-dimensional steady-state heat transfer. In the previously we have done the analysis of that Rajput book as 10th publication, and page number 16-17. I took that data for our comparing our theoretical Fourier law solution to our FEM solution. So I'll be keeping that only in mind and solving in a 3D way. So in APDL, there the construction of that model will be 2D. Now in this video, what we will be doing is we are creating that analysis on a workbench. So let me show you how. First, open the workbench and go for steady state thermal and drag it here. And go for engineering data. You have to open an engineering material and go for engineering data sources, and from here you have to select general material, and from general material you have to select copper alloy because it is carrying out a thermal conductivity of 370 watt per meter square. Okay, select this general material and your copper alloy will be appear here. So I'll be doing that only. So this is the copper alloy. Apply to add button, and you are applying add button, it will be added to our main frame of an engineering module where the static structural is defaultly present along with that. So it is added. Now go for engineering data source again, opening of previous interface. After opening previous interface, you have to generate a geometry. You'll see that you will be observing that in APDL our input parameter will be two temperatures and thermal conductivity for carrying out or calculating heat flow per unit area or heat flux. So I am going to calculate that only and comparing that result in this workbench. That will be somewhat same. I am considering here, I am giving it dimension such as length, breadth and height. In APDL I have given only height and breadth because height is I have given 100 mm and breadth is of I have given a length and height. Length is of 45 mm. So from here we have to go for XY plane, sketching, select a rectangle. First go for unit and select it millimeters. Now go for dimensions, general dimensions. This should be 45 mm and this dimension should be 100 mm. So and we have to extrude it. You can select any of the thickness because heat flux does not vary with thickness or length. It only vary with the length which we have provided here, 45 mm. So I'm selecting it as 15 mm. Now go for generate and you will see your 3D geometry is created. Now close this design modular and open module. This is the mechanical module in which we are pre-processing or applying a boundary condition on our geometry. So it is now open, steady state thermal mechanical. So here we have to apply boundary conditions. So go for geometry and select solid. First we have to apply a material, that will be a copper alloy. Now go for coordinate system. It is the meshing we have to generate here as as we have previously done in APDL. Now I'm going for sizing and give it as a medium, because the finer you created a mesh, the better you will be getting a result. So generate a mesh, we'll see mesh will be generated. All the entire domain is divided into small cubes that will be called as chunks. Now it is totally discretized into uniform sizes. It's time for steady state thermal. Now in steady state thermal we have to apply a temperatures at interfaces, two sides, because as we have selected, as we have give a copper alloy to our solid geometry, then this is the indication that thermal conductivity is automatically applied to this geometry. Now go for temperature, select here and apply 350 degrees Celsius is one side's temperature, and go for again temperature 2, this will be of 50 degrees Celsius, and click on apply. Now you will be seeing this is 350 degrees Celsius and this is 50 degrees Celsius. Now we have to calculate a heat flow, heat flux. Now go for solution, first solve it. So it is solved. Now go for inserting a result which we want. We have to see a temperature distribution and we have to see total heat flux. Now go for evaluate all results. Now all the results will be evaluated. Now the main function of this 3D environment, in APDL you cannot create animations, but here you can create an animation of a distributed temperature, how it is distributing. You can save it for your project purposes and your presentation will be perfect by showing this type of animation in the projects or any type of presentation. You will see the total heat flux will be 2.637 as we have calculated in APDL. So also you can put a probe, you can put a temperature probe entirely. I'm applying on this, and when you are evaluating a result, a temperature probe, sorry, this will not be affected from here. If you are using different types of different slabs, that then this result will be having a much more importance. But there is two of the results is important here, temperature and total heat flux. So in this way we have to do a thermal analysis. But you will see here there is a convection, radiation, perfectly insulated body, heat flux, internally heat generation. We can all put it together. In engineering you have studied heat and mass transfer. On that particular subject you have studied in first chapter conduction, and in second chapter there will be a convection and internal heat generation. So you can apply that theoretical concept and apply it in FEM software and see that your results are matching or not. You can explore yourself, and for better understanding you need to learn how to compare or how to use your theoretical knowledge and compare in a practical manner, because there is in industry there is no one has any time to calculate all this solution by hand. They are using only softwares, so you have to make yourself better in this type of softwares. So thank you guys, that's all for thermal one-dimensional thermal analysis. If you like this video, please share and subscribe with your friends. Thank you.